So we are discussing spectroscopy, but the instrumentation. And there are some common things that they all pretty much have. And the first being a little light bulb, or and more generally speaking, it's not always a light bulb though. Like, what does the FTIR use? Would a light bulb work for the FTIR? Is it interested in visible light? No. What's the infrared? So they have a glow bar, right? A hunk of ceramic or something that emits a wide range of infrared radiation. So, but in general, we just say a light source. Right, a light source. And in this case, I guess we're talking about UV vis, because look at all these different light sources, all these different wavelengths that are coming out, all these different colors. But after this black box, you only have one color. Then there's another black box. And now the intensity seems to have diminished. And the word they like to use with light is attenuate. So the light has been attenuated, and then it hits another black box. So this first black box seems like its purpose is to what? Right? Filter, yeah. Because look at all these colors you have, only one of them's coming out. So they're not gonna, you could use a filter. You could use one of those glass filter doohickeys, right, that only lets green light through. That would work. But if you wanna, you know, have an automated machine where you can let all these different wavelengths out, because remember, absorbance is measured at, how do you get an absorbance spectrum, right? It's what versus what? Absorbance versus, well, concentration would be a calibration curve. Wavelength, right? So you have all these different wavelengths, and then you get some blob or something, right? So the absorbance changes with wavelength. So if you want to get that, just think of all the bloody filters you'd have to have, because you have to monitor how things are absorbing at all these different wavelengths. You'd be popping in filters all the time. Now this, well, even they don't. No. So no, they're not going to use filters. They're going to use, starts with an M, monochromator. Right? So the black box is the monochromator. It's not going to be a black box for long, so we'll take a look at it. Okay, so the monochromator does its job. It selects wavelength. Now, if I could do things better, these two broad arrows, it shows that there's a high intensity of that lime green color, but I wish I could have them one a little bit shaded other than the other one, because it's a bandwidth that it's selecting. It's not selecting just 532.6 nanometers. No, the bandwidth is probably 530 to 535 nanometers. The whole thing looks green, but you have more than one wavelength coming out. There's a bandwidth there. But, okay, and we'll talk about that. But it probably hits what next then? Then it gets attenuated. This would probably be the, well, you got to put your sample in somewhere, right? Yeah, the little cuvette or the sample holder, your sample. So it might not always be a nice little cuvette, because look at the FTIR. You had this, if you've done that lab, you even had powders, diffuse reflectance accessory. You know, they can be pretty complicated, the little sample holder, but it's there. Every instrument has it, right? Okay, so the light passes through. If it absorbs, it gets attenuated. If it doesn't absorb at that wavelength, it won't get attenuated. Apparently here it absorbs. Then it must strike the, yeah, some kind of detector. Different detectors for different regions of light. Okay, so we'll start with the first one, light sources. We have continuous or discontinuous. Shelby, what's the difference there? Yeah. Like, which one would this one be? What's the difference? In mathematically, what's the difference between continuous and discontinuous? What does that mathematical term mean if you plot it out? Yeah, there's a gap or a break. Exactly. So what if you plotted out intensity, right, versus wavelength. Okay? If you have a continuous light source, there's just no breaks. So, I don't know, whatever. That's continuous. So a better light source might have it broader or wider or deeper, but there's no breaks. Discontinuous, right? There's breaks. I don't know. It could be here, and then there's another one, right? Or it could be, usually it's more like this. They're really narrow for discontinuous. What causes those breaks? Let's see. No, choppers for timing. So continuous or discontinuous light source? Continuous, right? And it's, I mean, it has an end, it doesn't go on forever, but it's continuous between those wavelengths. It's not all the same intensity either, but the point is there's no gaps. Continuous or discontinuous? Discontinuous. It's so extremely narrow, such a very narrow range of wavelengths. Okay. Now there's another one, discharge lamp.
So it doesn't have so much to do with the light source intensity or broadcast as much as it does with what the light source is broadcasting?
Exactly. That's exactly what it has to do with. Okay. And there's another one I'm going to show you. It's called a discharge lamp, but we have to wait just a little bit for it. We're almost there. The monochromator was the next part. Okay, so you have your light source, and it shines into this black box. And what's going to happen here is that I can sit there and rotate this grating, right? So what must this be? A mirror. Good, because you can see the other slit up here on the corner, right? So depending on how this is rotated, right, if I want to get that, I don't know, that orange light out or whatever, I guess it'd have to be almost like this. So then all those wavelengths are coming in, but only that orange. It's orange. I guess that's kind of orange. But they're all striking. All those colors are striking, right? They're all, I guess red, that'd be red, right? But they're just not making it through the slit. Right? They're just not making it through the slit. So when I was referring earlier about how I wish I could make these two colors be a little bit different shaded, yeah, because it depends on that slit width. Because what if that slit is a little bit wider? I'll get different colors of orange here. Oh, here's another orange, right? Some more, depending how that slit width is. And Bradley has played with slit width. In what lab?
The Planck's constant.
No, not that yet. In upstairs in 415.
Upstairs in 450.
You had to actually type in the slit width.
Oh, yes, when we were doing the atomic absorption.
The AA, yeah.
We had to practice with the various, the wider, let in more, let out more wavelengths.
Yeah.
So we could see more.
Yeah, because the lamps are dying and we're having trouble.
Yeah, the more narrow we got, the less we could actually
Yeah.
see.
Yeah, so you're playing with these slit widths. So this is essentially how a monochromator works, and everything is calibrated and controlled by the computer. If you go to that old Spec 20 and Gen Chem, there's actually a knob here, and you rotated it, and that rotated the grating to whatever wavelength you wanted to. Okay, now what I'd like to do is go check out Brad's PChem experiment. Now you can't touch anything though, right? Because it's all nice and calibrated, but he's got a monochromator over there, so let's go check it out. So we'll just leave everything in here. I guess I could take this. Okay, so let's leave the lights off. And let's come around over here. Now try not to bump the table, otherwise things can get messed up here. Whoa, gosh, it's dark in here, ain't it? Okay. Now how do we turn this stuff on? I turn that on. Let's turn this. Yeah, there he is. Didn't turn on. Where did we missing something here? Oh, maybe I turned this. Now do you turn on? There he goes. Oh, he's gonna take him in tomorrow. Okay, but we can take a look at the setup here. Okay, so you see that inside this box, so light source, right? It's gonna be one of those discharge lamps, kind of like we were talking about, and we'll see. But there's your slit width, okay, and then so you have this incoming light coming in. So the monochromator is getting to be over here, and here's a plastic doohickey hanging on the wall here. See that? There's your grating that the light's on, and then the light's passing through. All we're missing in our monochromator is the other slit hanging out over here. But on the wall, he's got it all. Can you see the lines? See the lines up here? Right? So you'd have to rotate that grating, and you could, with another slit, you'd have a monochromator. And so you see, but you can see the different colors though, right? Yeah. So would this light source be continuous or discontinuous?
Discontinuous.
Discontinuous. Yeah.
This is discontinuous?
Yeah, this would be a discontinuous light source. Because if it was continuous, you wouldn't have those black gaps. Yeah. It would just be a smear like that flashlight.
So even though
like this. You see the smear? Right? There's no gaps in between the colors.
So even though it's broadcasting each wavelength, like we see the orange, green, blue, that's not what's defining as continuous in this?
No, continuous or discontinuous is the output. And since this output, the reason why he's using this is that this is discontinuous. So he Googles it and he finds out what these colors are, the exact wavelengths. So now if he doesn't this is why we can't touch it. Because once he marks, oh, that's orange, that's green, that's violet, and just marks with a pencil, writes down the wavelength according to what Google says, he can shine whatever light he wants through here. And if that light strikes that position, he knows exactly what the wavelength is. So it's nice and calibrated. So that's why we can't bump anything.
I did mark it with tape just
So then what kind of compounds do you run through there to analyze? Or what samples do you shine in front?
This is just a mercury light.
Well, the objective of this isn't spectroscopy. The objective of this is to get Planck's constant.
Okay, gotcha.
Remember the equation for the energy of a photon?
Not really.
Energy equals little h times frequency.
Okay.
So that's a fundamental constant of nature.
Okay.
10 to the negative 36, a point with 35 zeros, right? And you can measure it just by doing this.
That is great.
So and it works really well. Okay, thank you. Let's click that off without bumping anything. All right. Thank you, sir.
That's good to know. We're going to work on that again in like an hour or two.
Yeah.
Try to finish.
It won't take too much longer. You just got to play with the LEDs. Okie dokie. So we've seen how monochromator works. The detector. So the last component. One of the most common I think one of the most common is on the calculator, diode array, but it's not sensitive enough for a lot of research projects, and to make instrumentation much more sensitive, they use a PMT, or photomultiplier tube. So I don't know if you can see this thing. Okay, so first so if you want to talk about your cuvette or whatever, that's going to be right in here. The light has to strike that silvery, shiny surface, right? So, and it's going to be really dark, so it's not very intense light at all. And it doesn't matter what wavelength either. So this, you remember the photoelectric effect. So light comes in, it can kick out electrons, but you have to reach some threshold. So this threshold on this is really, really low, extremely low. So I mean, any wavelength of light will just kick electrons out, because you don't want to be changing this for different wavelengths. That's a mess. So this thing it's always losing electrons. So when a photon hits it, the idea is photon hits it, doesn't matter what the wavelength is, it kicks out electrons. If more photons hit it, more electrons are kicked out. And then electrons are going to be detected. So look at all these electrical connections, though. And each one of these electrical connections goes up to, you see the little curvy copper doohickey? Okay. They call those dinodes. So a photon comes in, maybe kicks out a couple electrons. But electrons have what charge? Negative. So you can see it right there. There's the first one. So he's roughly maybe a positive 100 volts or positive 5 volts or something, right? So they're going to come in there, hit that. But he's coated with more of this stuff. So now you have some more electrons. So they're going to get bounced. So it's just like metal balls. They get bounced here. Now they're going to bounce down to the next dynode over to here, which has a little higher positive voltage, more emissive material. Now they bounce down to the next dynode. You just end up getting this chain. They call it a cascade of electrons. So that's what I want you to be able to draw here, right? Sketch what a PMT is. So pretty much how I like to do it is, first you got to have some hunk of this photoemissive material, right? I don't know.
In this case, it's copper.
No, it has to be a metal that, because copper doesn't kick out, it's going to take a lot of energy to kick out electrons from copper. So it's going to be I'm not sure what the indium, it's some weird funky metallic material that just kicks out electrons very, very easily. So you have a photon coming in. Let's say it's a red photon. That's my photoemissive material. Okay, and then you get an electron to get kicked out of there, I guess. Let's make them black. Ooh, a little electron gets kicked out, right? And then, how could we do this? Maybe, let's make it purple. All right, we have some dynode over here. Maybe it's positive, I don't know what their voltages are, how they step them up. You know, it gets pretty high, pretty dangerous. So positive 10 volts. And he's coated with more of that emissive material. Right? So now you get, I don't know, some more electrons getting kicked out of there. Right? They're going to the next dynode. Maybe he's positive 20 volts. Right? But he's got more of that emissive material on him. I didn't draw it very well, but and those are, you're getting some more to the next dynode, and it just keeps doing this. So just keep repeating this.
So all the green is that photoemissive
Yeah, I'm not very good at it, but that's the idea. That's the only way to get more of these electrons, right?
So just out of curiosity, this may sound silly, but since we're removing all of these electrons, would you have to decompose or something real fast?
Oh, I think no, it's going to last forever. There's going to be a problem, though. We'll get to the problem. And it just keeps going. I think what we don't realize is the sheer number of atoms and particles that are there, and how most of the stuff just sits around and doesn't do anything. It's extremely small fraction that's actually doing anything. Why isn't this? Oh, I keep pushing the wrong button. There's an easier way to do this. But just keep doing this, right? And the point is you end up with a cascade of electrons. Cascade of electrons, right? To your final one, that probably ends up being, I don't know, positive 500 volts or something, and you get your current. All from a single photon. Okay. So the more photons that are detected at the beginning, well, the more current you'd have.
Is that last one like the emissive?
I don't think so, because they just want it to end there. Who knows? Maybe in the manufacturing process, it's cheaper to have another one there. They don't care. I think that would add to the noise. I wouldn't think so. They want it to end. Now, a problem with this is since that material has to be so photoemissive and you want to detect a broad range of wavelengths, right? You want to detect a really broad range because your detector will be better than people buy it one. Well, that means it has to be even easier to kick out electrons. So heat itself kicks out electrons. So here's the signal, the background that's coming from a photomultiplier tube at negative 20 degrees Celsius, 30, negative 40, negative 50. So I don't know if you can see it very well. Maybe can you see it in your book any better? But the noise is worse at what temperature? Yeah. Right? Oh, I think I have the temperatures on backwards. Right?
Oh, it's supposed to be more.
Right?
Negative.
Oh, that's negative 50, not 50. Oh, okay. Yeah, they're negatives. Okay, it's getting colder. That makes sense, right? Because it's getting colder this way. That makes sense. I was thinking 50.
So the warmer the temperature, the greater the noise?
Yeah, and there's no photons even striking this. And it's just getting signal. So, and it's just, it's thermal energy just kicks out those electrons that are just released.
So for dark current, it's just that the electrons released from the thermal energy?
Yeah, from the photoemissive material. And there's no light even struck it. Yeah, so a lot of, if you want, we could have purchased a liquid nitrogen little deposition station for our UV vis and made it much more sensitive. And all it does is just makes the PMT cold. And you have to keep dumping stuff in there. But that's what dark current is called. Okay. So how could you minimize dark current? Cool it. Yep. Ooh, that's it. That's all for today.